Happy Tuesday. We are getting close to the end of applications of integration. All right. Today we're going to look at probabilities. All right, so when you actually study an advanced probability theory course, you find out that you have two types, right? You have discrete probabilities and continuous probabilities, right? So you should have actually looked at this a little bit in a standard intro stats course. Discrete probabilities are just sums, right? Because your set is finite or countable. And continuous probabilities are infinite and uncountable. Those are the ones we're going to look at because those are the integrals. Right? So what we're going to do for these first two is just verify that it represents a probability distribution function. Right, over the given interval, and then we will go ahead and determine the specified probability. So, a couple things that must be true to be a probability distribution function. Has to be continuous. So log of x over x squared is continuous on our interval. The values of f have to be between 0 and 1, which they are. And if you integrate the function over the entire interval, you get 1. Right, so that is what we're going to do. We're going to go integral over the interval, so 1 to infinity. Log x over x squared dx. And of course, this is improper, right? So we have to take a limit. Okay. Do u sub, so u is log of x. Right, that would mean that du is 1 over x dx. And x would be e to the u. Right, so we're going to get u over e to the u du, right? We're going to have a single x left in the denominator. We need to change our bounds. Log of 1 is 0. And then log of b. One. Okay. Just rewriting it as u e to the negative u. Formula number 42 on the integration table. It's going to allow us to take this antiderivative. What we get, negative quantity u plus 1, e to the negative u, right? And then that's going to be evaluated from 0 to log of b. Right? Get negative log of b plus 1, e to the negative log b. That's times 1 over b. It's going to be now plus, right? Because it's a negative out in front. 0 plus 1 is 1. E to the 0 is 1. So then just plus 1. Splitting this up into two limits, right? So obviously limit of a constant is just a constant. So now we're just looking at this limit here. Right, so a couple of ways we can go about this. We can just examine it, right? If you're familiar with how functions work, finding that limit is very simple. Or we can use L'Hopital's rule to take that limit. Right? Either way, you find that that limit is 0. And so we get 1. That is precisely what we wanted. Right, so since f of x is continuous from 1 to infinity, right, values are between 0 and 1. And the integral over that interval is 1. We conclude that f of x is a probability distribution function, which I'm going to simplify as PDF. Right? What they wanted now is to use that to find the probability that the random variable x is between 2 and 15. That probability is going to be given as the integral from 2 to 15 of the PDF. Right? From the work above, right? We know that's going to convert to the integral log 2 to log 15 of u e to the negative u du. To be e to the negative u. Right? Well, we know that's going to be negative quantity u plus 1 e to the negative u. Evaluate that from log 2 to log 15. I'm going to write it this way. Right, evaluate the first term at log 15, you get negative log of 15 plus 1 all over 15. Then it'll be plus log 2 plus 1 all over 2. Since we want a probability, we will approximate this to 4 decimal places in the rule of thumb. And so someone throw that into a calculator and tell me what you get as an approximation to 4 decimal places.
I got around 0.599.
Did it give you anything after that?
0.5994.
0.5994, right? So again, probability, rule of thumb, 4 decimal places. Right? Because that'll be 59.94%, and we typically go to 2 decimal places in percentage. That's just the general rule of thumb. Right, so that's the probability of a random variable taking on a value between 2 and 15. Right, now we're going to consider the function sine squared pi x over pi x squared. Right, over the interval 200 over 1059 to infinity. Right, so we look at this and we know it's continuous. We know that all the values are going to be between 0 and 1. Now I just have to see Does this equal 1? Do this by hand. Don't know if you can. And so doing this integral by hand is actually going to be quite the pain. I don't even know if there is a formula for it. Let's find out. Okay, so here's the trig integrals. UB. No, it doesn't look like there is. So I'm going to load up Mathematica. Magnification 150. Let's integrate. Let's actually zoom this in a little bit more. That should be big enough. What's sine of pi times x squared divided by pi times x squared? X goes from 200 over 1059 to infinity. Is this going to, or am I going to need to use n integrate? Let's find out. Let's execute. Yep, okay. All right, so that's definitely not working. So I'm going to use the n integrate command, which is a numerical integration. So there we go. It's about 1.00005. Right, so this is to 4 decimal places, 1. Right, so we can cough up the 0.0005 to the fact that we took a numerical integral. And we can just cough it up to approximation error. Right, so since f of x is continuous on our interval, right, values are going to be between 0 and 1 on the interval. Well, I'm just going to do it this way. I don't feel like rewriting that. I'm going to write it this way. And the integral over I of f of x dx is approximately 1. We can conclude that f of x is a probability distribution function. We now want the probability that x is less than pi over 6. Okay. First, the question is, does pi over 6 fall in our interval? Right, that's going to boil down to the question, is pi over 6 greater than 200 over 1059? I should be able to just test that. Right, I just test it in Mathematica. Pi over 6 greater than 200 over 1059. It comes back true. So we are in the interval, which is nice. Notice if it was not in the interval, then the probability would be 0. Right? So the probability that x is less than pi over 6 will be the integral from 200 over 1059 to pi over 6 of our probability distribution function. Right. Once again, this is going to be a really hideous integral. In fact, I believe it's impossible to do without PAS, so I don't know why I'm doing that. I'm just going to copy and paste. Let's copy, paste, and instead of infinity now, we go pi over 6. All right, so 3 decimal places, 0.6732. Or 67.32%. Okay. Right. Now, in the study of probability theory, there is one distribution that is really important, right? We spend a lot of time studying this particular type of continuous distribution function. Right? It is the normal density function. Right. Oh dear. All right. So I'm going to rewrite that function over here, I think. Given by f of x equals 1 over sigma times the square root of 2 pi e to the negative x minus mu squared over 2 sigma squared. Sigma is the standard deviation, mu is the mean. Right, and then x can be anything from negative infinity to positive infinity. Well, here's the problem. We're trying to find probability for normal distributions. There's the integral. That has no analytic solution. Right. And in fact, even if you write it as a standard normal, or not standard normal, I'm sorry, standard normal distribution where the standard deviation is 1 and the mean is 0, you still get an integral that has no analytic solution. Right. Now, in an intro stats course, you are given, if you've taken intro stat, a z-chart, right? And what you did in that course is you would just read from the z-chart to get your probability. What we're going to do is use Simpson's rule. Right, so we're going to do numerical integration to evaluate these types of integrals. And again, rule of thumb, 4 decimal places. Annual rainfall in inches for San Francisco is approximately a normal random variable with a mean of 20.11 inches and a standard deviation of 4.7 inches. What is the probability that next year's rainfall will exceed 17 inches? Now, this is what we're looking for. Right, so it'd be set up this way. Simpson's rule cannot be used on improper integrals. So we're going to have to do a little bit of analysis on this. I don't even need the chart. I don't need to plot it. I can just look at it from here. Do I want to write out the actual function? No. Well, notice something. $17 is less than the mean. Right, so we can split this integral at mu, at the mean. That integral is 0.5 because it's a normal distribution, right? Remember the bell curve. This is the mean. You have exactly 50% area on each side. So all we're really looking for now is this integral. So that is the problem that I'm going to set up for Simpson's rule. How do I want to do this? Define f of x as 1 over the standard deviation times the square root of 2 pi. Then it's times e to the negative x minus mean squared. I'm sorry. X minus mean all squared. Then divided by 2 times the standard deviation squared. Now I'm going to set my mean to be 20.11. I'm going to set my standard deviation as 4.7. Start of the interval is going to be 17. The end of our interval for Simpson's rule will be the mean. All right, so delta x, remember, is b minus a over n. I want that to be a function of n. Right, accuracy 10 to the minus 4. We want 4 decimal places. I'm going to start I off at 1. I'm going to start error at 1. Define S of 2. One third times delta x of 2 times f of a plus f of b plus 4 times f of a plus delta x of 2. All right, and then remember we did the while loop. Right, so while the absolute value of the error is greater than or equal to the accuracy, we're going to have it calculate S of 2 times I plus 1, right? We're going to say that is 1/3 times delta x 2 I plus 1 oops. I forgot to close it out there. There we go. Times f of a plus f of b plus 4 times the sum f of a plus j times delta x of 2 I plus 1 j goes from 2 to 2 times I plus 1. Another closing there. So that should take care of that. Plus 2 times sum f of a plus j times delta x of 2 times I plus 1. J goes from 2 to 2 times I plus 1 minus 2. 2 each time. I did forget that up here. Goes by 2. All right, that's going to finish up that sum. That's going to finish up that. Error is now going to equal. So 2 times I plus 1 minus S of 2 times I plus plus. And then we're just going to have it print ability is approximately S of, what did I do? 2 times I believe. I actually want numerical, right? Yes. The 4 decimal places. Okay. Now, what is that going to give me? Huh. Stuff I want to space there. Well, that is not what I got. Oh boy. I think I actually am gonna want. I don't know if this is gonna work. No, that's still not giving me what I want. Oh, crud. Where's my mouse? There you are. Why is that not working? Why is this mouse not working? No idea. That's annoying. Of course, I didn't save what I did. I definitely wanted this to be just 2 times I. Don't know. Why I'm not getting the answer that I got before. Oh boy. Right. Make sure I typed everything in right. So 1 standard deviation times square root of 2 pi times that to the negative x minus mean all squared divided by 2 times the standard deviation squared. Mean is 20.11. Standard deviation is 4.7. Yep. A starts at 17. We're going to go 17 to the mean, delta x. B minus a over n. Accuracy. 10 to the minus 4. Yes, that's right. 1/3 delta x 2 f of a plus f of b plus 4 times f of a plus delta x of 2 while absolute of average equal to accuracy. 1/3 times delta x 2 times I plus 1 times f of a plus f of b plus 4 times the sum f of a plus j delta x 2i plus 1. Oh, that's why. That should be j goes from 1 to... Perfect. Okay, now it's fixed. Simple fix. So the probability from 17 to the mean is about, and I don't know why it's giving me more than 4 sig figs when I specifically asked only for 4. What happens if I do 3? Still giving, I don't know why it's doing that, whatever. So the 4, it's what? 2, 4, 5, 9? Then plus the 0.5, you get a probability of 0.7459 or 74.59%. Excuse me, why is my mouse not working? As it's connected. No idea. All right. Anyway, excuse me for a minute. Okay. Let's continue. At birth, French citizen has an average life expectancy of 82 years with a standard deviation of 7. 100 newly born French babies are selected to live between 75 and 85 years. Assume the life expectancy is normally distributed. But what we're looking for first is a probability. All right, so we're going to need this probability. And I think for this one, since it's now off screen, I am going to actually write it out. So it'd be what? 1 over standard deviation, 7 times the square root of 2 pi, integral from 75 to 85 of e to the negative x minus the mean, which is 82 all squared, divided by 2 times the standard deviation squared. I'm just going to go back to my code. Right, we just have to change a few things. Right, the mean is now 82. Standard deviation is now 7. A is 75. And B is 85. And that's all we had to change. Right, so about 0.5072. Right, which is 50.72%. But that is not what was being asked, right? We're being asked specifically of the 100 newly French-born babies, how many would we expect to live between 75 and 85 years? So what do we think based on this?
It'd be around like 51.
We would expect 51 of the 100 to live between 75 and 85. Right. In this case, context is everything, right? It wouldn't make sense to say 50.72, right? Because what is 0.72 of a person, right? So we just round it up to 51 and say about 51. And we got one more. Team of medical practitioners determines that in a population of 1,000 females with ages ranging from 20 to 35 years, length of pregnancy from conception to birth is approximately normally distributed, a mean of 266 days, a standard deviation of 16 days. How many of these females would you expect to have a pregnancy lasting from 36 weeks to 40 weeks? So what we're going to do is I'm going to write out f of x for this one, right? So it's going to be 1 over standard deviation, which is 16 days times the square root of 2 pi, e to the negative x minus the mean of 266 days squared all over 2 times standard deviation, which is 16 squared. All right, so we want a probability of pregnancy lasting between 36 weeks and 40 weeks. So it's clearly going to be an integral of f of x dx. But notice that the mean and standard deviation here, they're given in days, right? Not weeks. So you have two choices. Convert the mean and standard deviation into weeks, or convert the weeks into days. I think it's easier to convert weeks into days. So we're going to integrate from 36 times 7 to 40 times 7. Please, thank you. Right, so again, if I come back to code I already wrote, change the mean to 266, change the standard deviation to 16, change A to 36 times 7, change B to 40 times 7. Right, and that's all that we need to adjust. Now, if we just execute it, we get 0.6184. Right, which is 61.84%. Right, so of the 1,000 females, we would expect 618 of them to have a pregnancy lasting between 36 and 40 weeks. Any questions on probability? Okey-dokey. So what I'm going to do is just end it there. I didn't actually write a quiz for probability, so there's no quiz on this. On Thursday, we are going to look at work. And that's probably going to be it. So the next two lessons are going to be physics-based. Right, we have two applications left to look at, work and center of mass. Thursday will be work, and then when we get back from spring break, we'll do center of mass. So the second test will be after spring break. Right. Have a wonderful rest of your day. See you Thursday, hopefully, back on campus.